also. So sector 1 here, again the phase A and C are the control phase. Of course, the current polarity, we can see that one. A is the positive, but A is negative and C is positive. A current through the phase A, injected current, that is negative, but this is the positive, meaning that SAN and SCP. Clear? SCP and SAN, or SCP and SAN. Actually, this is the buck topology and this is the boost topology. It is a buck boost topology. Actually, the power flow based upon the power factor angle, the real and reactive power flow will be varying. Okay, therefore the phase A is the buck topology and phase C is the boost topology, and the totally it is a buck boost topology, in which if the power factor angle is other than, of course, 0. 90 degrees dual boost topology, and if it is 0, it is a dual buck topology, and if it is any other angle, it is working as a buck boost topology. One phase will be bucking operation, another phase will be boosting operation. Of course, the power factor angle will be deciding how much it is bucking and how much is the boosting. But anyway, topology is that buck and boost topology is to be automatically the inverter is taking this topology. Clear? For this is the for a power factor angle equal to 60 degree, and this is for example, a reactive power compensation is also can be done. If you are injecting a current 90 degree out of the grid voltage, it can inject the reactive power. It can inject the reactive power. Again, the topology is based on the, as I told you, these are two principles. Sector, you identify the sector, then you can identify the phases that will be controlled. First phase. Second, you have to identify the polarity of the injected current. If the polarity of the injected current is positive, top switch is being controlled. If the polarity of the current is negative, bottom switch is being controlled. Based on that one, you can make the corresponding topology. Like in this case, this is the 0 to 30 degree, this is the topology, and 30 to 60 degree, this is the topology. Both are buck and boost topology, but the switches are different here. Therefore, automatically the three-phase grid inverter is taking the different topology based on the phase angle of the injector current with respect to the grid voltage. Therefore, that is shown as that one. Different topology it is taking. If it is the phase angle, injected current phase angle equal to 0 with respect to the grid voltage, it is a dual buck topology. If the injected current is 180 degree with respect to the grid voltage, it is a dual boost topology, dual buck. And all other things, it takes a buck and boost topology. Based upon the phase angle, the switches will be different. Therefore, this is the way in which it can be at any instant. I'm telling that at any instant, only 2 switches are being controlled at a frequency. Out of the 6 switches of an inverter, 3-phase inverter, 2 switches are being controlled at that frequency. Therefore, the switching loss is reduced much. That is the advantage of my proposed, of course, switching method or algorithm. Therefore, I told you, one thing is that you have to identify the sector. Sector identification is crucial. Whether it is grid voltage is 0 to 60 or 60 to 120 or 120 to 180, 180 to 240, 240 to 300 or 300 to 360. 6 sectors are to be identified. Therefore, there is a voltage sector identification is there. Of course, very easy only thing. You are taking the zero crossing detector and based on some logical method, we can identify which is the, for example, in this case, 0 to 60 identified, phase A and C are rectified. Phase A is taken as well as C is taken, and that is ANDed, that is logically ANDed. Then you'll be getting the corresponding to T1. Like that, you can, by logical method, you can identify the sectors that do the instant sector identification. T1, T2, T3, T4, T5, that can be identified. Or T1 means 0 to 60, T2 means 60 to 120. Like that one, T6 is 300 to 360. The sector identification can be done by, this logical method that can be derived by using the software, or by discrete components also can be used. Therefore, as I told you, sector, this is the zero crossing detection of the phase A, and this is the zero crossing detector of the phase C. If you are logically ANDed, if it is being ANDed, you'll be getting the correspondingly, this is the sector. This is corresponding to sector 0 to 60, and this is corresponding to sector, of course, 120 to 180, like that. Therefore, we are using the different Boolean logics and to identify the voltage sector. That is the first thing we have to do. Second thing is we have to identify the different sectors like T1, T2, T3, T4, T5, T6. Like that, different sectors can be identified. Second one is the reference current polarity is to be identified. Reference current polarity means, I just told you, which switch is in a phase is decided by current polarity. If current is positive, top switch is being controlled. If current is negative, bottom switch is being controlled. Therefore, current polarity is very important. That is based on that one, will be select the switch. Therefore, here a reference current is, of course, that is compared with a zero constant detector only. We'll be getting XA, XA dash, XB, XA. There are certain logic is the current polarity. For example, if it is a positive current, XA will be 1 and XA dash will be 0. Like that, IB is positive, XB will be high or positive 1, or this will become 0, like that one. That logic is derived. So that is again that the current polarity, that logic is derived by using this reference current polarity. And there are certain method is that this is actually there are some logical equations are there, and that is in the inside the books. That is, I mean, T1, T2. That is to that one. What the inputs are? One is the voltage sector identifier, which sector is to be identified. Second, current polarity identifier, about current which is a positive or negative. These two things will be deciding what are the switches to be controlled. Clear? The current polarity identifier output as well as voltage sector identifier T1 to T6. These two parameters will be deciding out of the 6 switches which switches are to be controlled. Clear? Now here I am using hysteresis current control only. In that one, this is the 3-phase inverter and the DC bus voltage that is compared with the reference voltage, and the error is taken, that is given to a PI controller, and that PI controller output is being multiplied with a unit magnitude 3-phase sinusoidal signal. For example, if you want to inject a current in phase to the grid voltage, clear? If you want to inject a current in phase to the grid voltage, you'll be making a unit magnitude sinusoidal signal which will be in phase to the grid voltage. Clear? If you want to inject a current in phase to the grid voltage, this unit magnitude signal you are making, that is PLL, you can use PLL, that is made in phase to the grid voltage. Therefore, this will give only the phase information, and the magnitude information will be given the output of the PI controller. Therefore, multiplication of that one will give the reference currents in phase A, phase B, and phase C. Actually, I have done for a constant frequency application, constant frequency hysteresis controller. I will be subtracting with a triangular. I have not explained that one. I might. My work, I have made the hysteresis control with a constant switching method. Therefore, anyway, these are the reference currents, IA reference, IB reference, IC reference, meaning that this much current is to be injected in each phase. In order to get the reference current, what method we have done is that we will be comparing the actual DC bus voltage with the reference voltage, and that is multiplied with the unit magnitude signal. And that will give the reference signal. That is being compared with the actual signal. As I already hysteresis current control, I told you, that is given the switching pulse AP, AN, BP, BN, BCP. And the switches that is to be controlled is decided by this voltage sector that is given to this switches, 3-phase inverter. And so that the current that will be controlling the inverter, so that much current will be injected into the grid. As an example, if you are making this current in phase to the grid voltage, this will be working as the, of course, in phase 2 means that this will be working as an inverter. The power flow will be from the DC side to the grid. Now, if you make this unit magnitude signal 180 degree out of phase with the grid voltage, then this gives a phase information. Then this injected current phase angle will be 180 degree out of phase the grid voltage, so that of course, this converter will be working as a rectifier. In that case, the power flow will be from the AC grid into the DC source, or if a battery, it is a battery, it comes. Therefore, any power factor, for example, you can make this phase angle of this one, any angle, so that the real and reactive power flow between the DC source and AC grid can be controlled by this converter. And of course, my proposed one is that at any instant of time, only 2 switches are controlled at high frequency, so that the switching loss is minimized. That is in my proposed thesis, that is the identification, or that is being proved as such. Switching loss is minimized by controlling only the 2 switches at any instant. Fine. Okay, fine. One more thing. Okay, 6:30. For the simulation result, I have just thinking. For the grid connected, if for example, actually I have done the simulation as well as hardware I have done. Here, this is the injected current is in phase to the grid voltage. As I told you, if the injected current is made in phase to the grid voltage, it is working as an inverter. The power flow is from the DC source into the grid. The converter is working as an inverter. Okay. It is working. Actually it is the battery to the grid, vehicle to the grid. We can say that vehicle to the grid, V2G transfer. If in a EV case, it is a V2G vehicle, because battery is there, that is transferred to the grid. V2G transfer. That is, in that case, the power factor angle equal to 0 degree. Of course, the injected current is in phase to the grid voltage. And if you make the, okay, you can have any angle that I done, 60 degree lagging, so that the real and reactive power can be injected. And 180 degree out of phase. The injected current is made 180 degree out of phase the grid voltage. In that case, the power flow is from the grid into the battery, or G2V, grid to the vehicle. In the power is flowing from the grid into the battery, or grid to the G2V. In order to have a power flow from the grid into the battery, simply what we are doing is that we are making the injected current 180 degree out of phase with the grid voltage. Of course, that's a phase angle. Of course, the magnitude will be deciding the magnitude of that real power transfer. For the reactive power compensation also, then we can have a reactive power compensation so that power factor can be improved. Therefore, here a bidirectional power, just an example I just shown, the phase angle that the injected, these are the phase angle of the injected current with respect to the grid voltage. With respect to grid voltage. For a grid voltage of 115 volt per phase voltage and injected current of 10 amperes per phase, and the real power, you can say that one, if the phase angle equal to 0 degree, this much real power is being injected. Of course, reactive power equal to 0. If you are making the phase angle to 60 degree, this much real power is being injected. Power is flowing from DC to AC itself, and this much is also reactive power is being injected. But if you make it 120 degree, can say that one minus 17, or this much real power is taken from the grid into the DC source. And of course, this is the reactive power supplied. And like that one, if it is a 180 degree, means that this much 3450, that much real power is flowing from the grid into the DC source, or it is working as a rectifier. Of course, the reactive power equal to 0. Just to show that one, by controlling the phase angle of the injected current with respect to the grid voltage, you can vary the real and reactive power control between the DC source and AC grid. Clear? Basic concept is clear. Hopefully understood. If any doubt is, you can ask. Therefore, this is the transient response behavior. Suddenly it is changing the mode as such. Until this one, it is working as the current injected is in phase, that is working as an inverter, and this is working as a rectifier. That is transient behavior. You can see this is tracking to the at the instant 0.035 seconds. Suddenly mode is changing from the inverter to the rectifier mode. And then again, switching loss is calculated. This is the conventional method of the switching the voltage. Of course, this is the switching loss. There is switching signal to the. These are switching signal actually. The switching signals to the switches. But this is the, for example, this is the next one is the dual buck configuration and dual boost configuration and buck and boost configuration. We can see that in that case we can that the switching signal duration is getting reduced. Of course, the switching loss is reduced by that method. And if you calculate, to calculate the switching loss, as you know that one, to calculate the switching loss, we have to plot what is the instantaneous value of the voltage across the switch, what is the voltage across the switch, as well as what is the current through the switch. Take the product of that one, you'll be getting instantaneous power. You take the average value of that power, that is the switching loss. This is for of course, the conventional method, or if you the method that is what I propose, that dual buck topology and dual boost topology, like that one. In that case, we can say that switching loss is reduced, because this is the of course, the average value of this one is called the switching loss, or switching loss is reduced much if you buy this method, because at any instant of time, out of the 6 switches, only 2 switches are used or are switching at high frequency. And I compared with the reduction in the proposed control scheme, the losses, and there's a dual boost and dual buck topology. There's a reduction loss is given here compared to this is conventional control with a constant switching frequency. But with a modified hysteresis control with a constant frequency, this much reduction in switching loss is the percentage wise. This is the percentage reduction in switching loss. Anyway, the efficiency of the converter is improved. And that is marked as a compared as a switching loss. In a I told you a different topology. I told you, you hopefully understood now. The inverter is taking different topology like dual buck topology, dual boost topology, buck and boost topology. Like the different topology automatically takes. That's a meaning that three-phase inverter is automatically converted to that topology. And the switching loss corresponding to different, of course, the topology for the conventional component and proposed one. That is, in proposed one, the switching loss is reduced much. The basic concept of real and reactive power control between DC source and AC grid that I explained, and a concept of hysteresis current control also explained for bidirectional power control, and a switching algorithm for bidirectional power control also explained. And switching losses are reduced because of only two switches are controlled at any instant of time. Current injected into the grid is in phase to the grid voltage in inverter mode of operation, and 180-degree out of phase with the grid voltage in rectifier mode of operation. And design and implementation of control circuitry and implementation of the bidirectional real and reactive power control, that is also explained. Okay, that's all what I reference it is. Basically, I followed the Nat Mohan books, that is for explain the first portion. No, I use that Nat Mohan books only. Basic concept of that is the I explain. No, that is if you understood that concept, it is well and good, because that is the basic concept I'm telling. That is how you can control the power flow. I mean, of course, how you can control the power flow between the AC source and DC grid. That is basically you are controlling the converter, one both magnitude and phase angle, or in a way, another way you can tell that you are controlling the voltage across the linking inductor. You are controlling the voltage across the linking inductor, because that will be deciding, of course, the magnitude of the source current as well as the phase angle of the source current. As VL changes magnitude, because VL is changing, see that one? VL is changing like that one. ISN also changing that one. The magnitude as well as, of course, the phase angle of this source current. Of course, source voltage, you don't have any control. This is fixed. Only you can control only the magnitude of the source current as well as the phase angle of the source current. That is only you can control. By doing that one, you can have a control of real and reactive power control between the AC grid and DC source. For this, you should be aware of this. This concept is, if you understood, it's well and good. Therefore, this is the basic principle. Okay, you can refer Nat Mohan's book. If any doubt is there, you can. Okay, thanks a lot for the patient listening. If you have any doubt, most welcome. Dr. Eugene.
Sir. So the participants, if you have any doubt, please you can ask. Sir is detailing a very component, I think, in detail presentation.
That is, if you want, okay, you can ask if you want. You understood? Could you follow me this one? Basic concept. First I explained based on the Nat Mohan. Second phase I explained based on my work. How you can control the real and reactive power flow between the DC source and AC grid. In a three-phase case I explained, that's related to my PhD work. And the first one what I explained is based on the Nat Mohan's books, written in the Nat Mohan books. That is basic concept, utility for control of that one. Okay, any doubt is there, you can ask.
Good evening, sir.
Yeah, good evening.
So the concept is very clear. So I have a doubt. Is it possible to implement the same technique in single-phase grid-connected system?
Which one? What I explained there, no?
Yes, sir. Yeah, you are implementing the three-phase system.
Yeah. Okay, I don't think. What I explained is that out of the 6 switches, I'm reducing the switching, switches like that, 2 only controlling at a, because why I'm using that one is that the controlling 2 phase in a 3-phase system, if you controlling a 2 phases, automatically 3rd phase gets controlled. Even 4-phase system, that concept cannot be used. But I explained that. if two phases are being controlled, that automatically controls the third phase, three-phase, three-wire system. Therefore, that what I explained is that concept is for a three-phase, three-wire system only.
Sir, if we are applying this concept to any system, is it needed to convert the voltage to a unit vector? Magnitude is needed to convert it in
Okay, no, the concept that's correct. If you are my concept, I'm telling you, no, if you are injecting a voltage, if you are injecting a current which is in phase to the grid voltage, it is basically you are making the converter as an inverter. The real power is flowing from the DC source into the grid. No reactive power. Clear?
Yes.
Now, your question is that, unit vector. Okay. Now, say, I'm telling that if you reverse the unit vector polarity, you can inject a current which is 180 degree out of phase the grid voltage, then the role of the converter is being changed. That's what I'm telling. The converter is now working as a rectifier. In that case, the power is flowing from the grid into the battery. That is, I'm telling, that is vehicle to grid. The power transfer is like that one. That unit vector unit vector phase angle decides the phase angle of the injected current.
Okay, sir. Only
Okay.
phase angle. Okay.
Yeah, correct. Yes. Phase angle, that's okay. Just one second. I'll bring that one. Here, this unit magnitude sinusoidal signal, no, that decides the phase angle of the injected current. Clear?
Yes.
Magnitude will be decided by, of course, the reference voltage and actual DC bus voltage error given to the PI controller, etc. Therefore, this will decide the magnitude and this will decide the phase angle. Yes. The product of that one automatically decides the reference current. This is the current to be injected. You hopefully understood the Hister's current concept, no?
Yes, sir.
Hister's current, okay. Then this is the reference current, means that actual current will follow the reference current, so that if you want to inject a current in phase to the grid voltage, you make it this unit signal in phase to the grid, then the current will be injected in phase to that. This is then the converter is working as an inverter. Now, if you want to have a reverse power flow, you make this unit sinusoidal signal 180 degree out of the grid voltage, then the power, the injected current will be 180 degree out of the grid voltage, or the power will be flowing from the grid to the DC source, or this is working as a rectifier. The converter role you can change. In between, any power you can change. Say you can, if you make any angle, then you can have a real and reactive power control. You can have this much. For example, if you want to make a reactive static war compensator, like you want to compensate the reactive power, you make this unit magnitude signal, this one 90 degree out of the grid voltage. This unit, that's what I'm telling. This unit magnitude signal will be deciding the phase angle of the injected current. If you make this phase angle 90 degree out of the grid voltage, the injected current will become in 90 degree out of the grid voltage, or that is the reactive power will be injected.
Okay.
That is then the converter is working as a reactive compensation, static reactive compensator, war compensator.
Okay, sir. Thank you.
Basic concept is clear. Basic concept is clear, no?
Yes, sir.
Then the switching laws, regarding the switching laws reduction, that is my, of course, PhD work as such. That is at any instant of time, or that's why I explained the three-phase, three-wire system. At any instant of time, two switches will be controlled at high frequency, so that the switching loss is reduced much, so the efficiency of the inverter increased. Yes, sir.
Thank you, sir.
Okay, thank you. Welcome. Any more question you can ask, because don't have any hesitation. I'll be trying from the fundamental. Once the fundamental is clear, no, you can build up. That's our main concept. And I used to, in that way, I used to take the class. Fundamental should be clear. Especially this, no, this one, this is that's clear. You can explain even I mean, I think in Natmohan, the derivation is not given. I don't think Natmohan is, but the concept is given very clearly. It is given. Derivation that the real and reactive power derivation, no, that you can take this one. This is a real power and reactive power flow from the AC grid and DC source.
Sir,
Yes.
as
Yes.
the time is very short because we have a test which is
Yeah.
starting at 6:30.
Yeah, sure. Okay, no problem. That's I'm trying to maximum. Okay, our correct time, no, 29, 6
Yeah,
29.
yeah. Sir, okay, so we are moving to the conclusion of the session. So I invite Alim to hand over the session.
So, thank you so much, sir, for sharing your valuable insights and expertise with us. So, as a token of our appreciation, we take this moment for the virtual presentation of a memento and certificate to our esteemed speaker, Dr. M. Nandakumar.
Thank you. Okay, thanks a
Thank
lot.
you.
Thanks a lot. Thanks a lot for the coordinators for giving me a chance to share my, of course, whatever the topic I covered, no, to share my colleagues like that, of course, colleagues only.
We also thank Nandakumar sir for taking time and giving very much effort to taking this session very detailed manner. So indeed, it will be very helpful for the research scholars as well as the faculties who are doing research in this area.
Okay, thanks a lot. If at all any doubt is there, you can contact me. I can give more inputs to that one. Okay, thanks a lot.
Okay, sir. Thank you, sir.
Okay, fine. Thank you. Shall I leave?
Yeah, sir.
So, not say your exam, no? I mean,
yeah, participants, please note now our exam will start from 6:30 to 7:30. There is after 7:30 the link will be disabled. So please attempt your test within this 7:30. Please complete your evaluation with 7:30. And after that, you can complete the feedback also. In the portal itself, there is a link called feedback. So in that feedback session, feedback also you can complete. So if the time permits. Okay. So please go through the question. And
Dr. Eugene, I am leaving, no?
Okay, sir.
Okay, well, thanks a lot. Bye.
And if there is anybody from your institute who are participating in this FDP and cannot be able to attend today's session, you can share the information to them also. I have mailed and put a notification to all the mail IDs who have registered. That means I got from the portal. So you can also remind them the time is from 6:30 to 7:30. After that, there will not be any link. So if you are not attending the test, then the certificate will not be issued from the Atal, Aicte-Atal portal. So Aicte is giving the certificate. So this certificate issued only for the participants who attend, who made attempt to this test and scored the good marks. Okay, thank you all. So if there is any doubt, you can contact me on WhatsApp. So there will be a valedictory session at 7:30. So you can join at 7:30. Hello. Anyone talking? Oh, no. Devanshi, do you? Devanshi is there?
Yes, ma'am.
Okay, can we start the valedictory function? So, I officially invite you all for the valedictory function of AICT online FDP on electric vehicles. So, over to you, Devanshi. So before starting, there is a problem with the assessment session and the feedback session. So we will raise the issue or we will report the issue to the AICT portal so that we will have another arrangements for this assessment. Either we will give a Google form in a pre-scheduled time. So we will inform you tomorrow or day after tomorrow, because the working day will come on day after tomorrow. So we will inform you. So over to you, Devanshi.
Okay, ma'am. So, good evening, everyone. Today's valedictory function will be held by Ardra. She will be the official anchor today. Ardra, please, you can begin now.
Thank you, Devanshi, for inviting me to this particular session. And good evening, everyone. I'm Adra Sunil, and it gives me great pleasure to extend a warm welcome to all of you to the AICT Training and Learning Sponsored Online Faculty Development Program on Emerging Trends in Electrical Vehicle Ecosystem, Power Electronics, AI, and Sustainable Mobility, organized by the Department of Electrical and Electronics Engineering of Christ College of Engineering. So, before starting, may I know if I'm audible? Excuse me?
Yes, Ardra, you are audible.
Yeah, sure. So we are truly honored to have with us distinguished dignitaries, eminent speakers, respected faculty members, and enthusiastic participants joining us virtually from different places. And today marks the ending of an enriching journey of learning and knowledge sharing in the field of electric vehicles and sustainable mobility. So to begin the session on an auspicious note, let us invoke the blessings of Almighty. I request everyone to kindly join for the prayer. And I invite Diana Reggie for the prayer.
Light of the world, you step down into darkness. Open my eyes, let me see beauty that made this heart adore you. Hope of a life spent with you. Here I am to worship, here I am to bow down, here I am to say that you're my God. You're altogether lovely, altogether worthy, altogether wonderful to me.
Thank you, Diana. And now I take the privilege to invite Dr. Eugene Peter, the coordinator of AICTE ATL Online FTP 2025, for the FPD report presentation.
Let me share the slide. So welcome to the FTP report on 6-day AICT-Atal training, Atal online training on emerging trends in electric vehicle ecosystem, power electronics, AI, and sustainable mobility. We thank the AICT as well as the Atal team for sponsoring this event, as well as the Christ Engineering College for giving support for this AICT training. So we have from day 1 to day 6, we have eminent speakers. So the FTP is inaugurated by Dr. B. Subbareddy, Chief Research Scientist, Indian Institute of Bangalore, and followed by the keynote session in various topics. Dr. B. Subbareddy delivered the seminar on electric vehicle, battery issues, and portable solution. Then comes the Dr. Srijit S. of NIT Silchar. Then Dr. Rudra Sarkar of NIT Mizoram. And session 4 is handled by Dr. Amitesh Kumar of NIT Patna. And from the industry side, we have Dr. Devanand Singh Dio from MathWorks and Professor Dr. Maladi Batumalai from Malaysia. She handled the topic AI and IoT in EV monitoring and predictive maintenance. And from Intel Technologies, engineer Alex J. Paul joined us with the topic EV communication protocols and cyber security. And from ISAB India Limited, R. Akhil Raj deals with the topic BLDC motor for EV. And Dr. Arun Eldo Elias, who is an entrepreneur as well as the faculty, deals with the topic startups and innovations in EV value chain and regarding the policy for developing the startups. And from Columbia Lab Private Limited, Liju George T, engineer Liju George T, deals with the different charging infrastructure, the rise of EVs and charging infrastructure, particularly in Kerala. Then Today we have the sessions by Dr. Riaz A. Rahman of MathWorks Product and Dr. T.D. Subhash from Zhejiang Ocean University, China, and Dr. M. Nandakumar, Senior Professor of Christ Engineering College in Nalgunda. I extend my sincere gratitude to all the resource persons. So the participants profile, coming to the participants profile, number of registrations is 129 and almost 90% have attended the session, and faculty of this registration, 82% are the faculty members and 12% are the research scholars and 8% comes from the industry experts, industrial person. So the FDP outcomes are the participants as well as the those who participated. It is open call for everyone. If the webinar or the LCD, this FTP is open for everyone. We have provided the YouTube live stream also. So the participants will get enhanced knowledge on EV technologies, and there will be a new topic which is emerging in EV technologies, which is the integration of AI and IoT. So here in this FDP, we have we are dealing with the topics AI and IoT integration in EVs. And we have included one of the session as startup and industrial perspectives related to EV field. And there is a hands-on session we planned, but in the online mode, it is difficult. So the experts made a hand-on session, in detail presentation of MathWorks tools by 2 sessions. Then the last session, that means the last day session deals with the research and collaboration opportunities. So we acknowledge AICT and Atal Academy for the sponsorship, and as well as the management and principal for Christ College of Engineering, and the resource persons and experts for their sharing their valuable knowledge, and the organizing team, entire EEE department for organizing this event very efficiently, and the participants. We acknowledge the participants for active involvement. Thank you.
Thank you, Eugene ma'am. Now I welcome forward Dr. T.D. Subhash, our chief guest for the day from Zhejiang Ocean University, Zhejiang, China. It was incredibly an honor to have him earlier, to have a session from him, and it was just an heartbreaking section as it led to the knowledge as well as to the experiences for the faculties as well as to the other people who have attended the session. I welcome him forward to speak few words for today's session.
So thank you, Adra. Great things happens when there is a gathering of great minds. Great things happens when there is a gathering of great minds. Warm good evening to all. First of all, I appreciate and congratulate AICTE and Government of India for providing financial support to host this particular FDP. So even though AICTE is providing opportunity and initiatives, but the responsibility of the management of particular engineering colleges to motivate the faculty members to take the initiative, to submit the application. In that case, I congratulate the management, the principal of Christ Engineering College for motivating the faculty members to submit applications. And again, I congratulate the Department of EEE for organizing such event. A special congratulations goes to the coordinator, Dr. Eugene Peter, for submitting the application. Because the problem is when you're submitting the application, the same expert should be attend the section. So that is very critical. It's very crucial. So because we can't, without the consent of the resource persons, we can't submit the applications. And I'm happy to see a lot of resource persons from national institutes, industries from abroad. Because getting contacts or getting resource person from abroad is complex because the time is crucial actually. The time zone get varies. So, and we can't directly call them. We need to call them by WhatsApp calls, etc. It's very crucial. So in that case, the organizing team done a wonderful job. So you might say that the past 1 week, the program is there. They are follow all those things, but the program not stops here actually. because you see the programs completed, but their works need to till they get the reimbursement. So because next another couple of weeks or 1 month, they need to submit all the reports and bills to the Atal, Atal Academy of AICT. Then they need to follow till the amount get reimbursement. So it's a great task actually. So being an organizer, I know that difficulties. So my special congratulations, appreciation to Dr. Eugene Peter and the team of electrical department, including student volunteers. They have done an amazing job, because I know that it's not an one-man show. There is a team behind this wonderful event. And next is regarding the question among the faculty fraternity that whether AICT will replace the faculty members. So whether AI, artificial intelligence, will replace the faculty members. Will take the teaching job. It's not possible. But the faculty members need to use AI in teaching. So this is the concept behind that. Then related to the faculty members, as well as the participants, I convey a short note to the organizing team. So you need to create a rapport, or you need to get the contacts of all the participants. I need to create a database, and you should have the get a clear rapport with them. So by getting feedbacks, so I request the participants to provide positive feedbacks, so that if there is any problems or any negatives, it can be overcome in the future events. And the success of this event will comes when the faculty members take this condensed to the students, and they need to develop some projects and publish papers and publish patents. So that is a success of this event. It's the motto of this particular event. And when the organizing team get rapport with the participants, from this 128 participants, at least one faculty member will publish papers as well as file patents. Then please share those things with the organizing team, so the organizing team can make a success stories in the future events, and they can appreciate the particular participants. This is my personal request to the organizing team as well as the participants. Once again, I thank each and everyone for this wonderful event and giving me an opportunity to share my thoughts. To conclude with a quote of Mahatma Gandhi: dear faculty members, be the change that you wish to see in the world. Be the change that you wish to see in the world. Thank you all.
Thank you, sir. It was a wonderful remarks from your side. Now I welcome the captain of our ship, our principal, Dr. Sijo MT, the principal of Christ College of Engineering, to mark our remarks on the session. Sir, please come forward.
Am I audible?
Yes, sir, you may proceed.
Okay, thank you. Good evening, one and all present here. Respected chief guest today's evening, Dr. T.D. Subhash sir, and their organization of this 6-day Atal FTP. As we reach the culmination of 6-day FTP program on emerging trends in EV technology, I take this opportunity to congratulate all the participants. I happen to know that there are 129 participants are there for successfully completing this 6-day FTP. As our chief guest mentioned, they should have some outcomes of these type of FTPs, like publication of papers and sharing your knowledge with students. So these things should happen after this FTP. So then only we can say that this was a successful FTP. And I take this opportunity to congratulate electrical department, especially the head of the department, Needu Varghese ma'am, Deputy HOD Nidin sir, and the program coordinators, UG ma'am and Vishnu sir, and all the faculty members of EEE department and all the student volunteers taking all the pain to complete this 6-day FTP. Then I take this opportunity to again congratulate, and I take this opportunity to say thanks to the CC management for providing all the things for the successful conduction of this program. Okay, with this I conclude. Thank you all.
Thank you, sir. Thank you for your words and remarks. I now welcome forward Professor Nitin KS, Deputy HOD of Department of Electrical and Electronics Engineering, to address the overall event. Sir, please come forward.
Yeah, thank you. Is it audible?
Yes, sir, you may proceed.
Okay, thank you. So, respected Chief Guest of the day, Dr. T.D. Subar sir, and the Principal Dr. Sijo sir, and the coordinators, and all the faculty members and the participants. So actually, over the past few days, we have had the opportunity to engage with experts, mainly from these electric vehicle areas. As we know, this electric vehicle sector is an emerging area where there is a large scope of the research and all. Okay, as we know, in the coming years, the number of electric vehicles is going to be great. Okay, so our department, the electrical department, is gotten. There is the second chance we are conducting such another FTP. So the coordinators made a wonderful effort here, mainly Dr. Eugene Peter and Dr. Vishnu Patnaban sir. So actually, I congratulated these two persons. These are the main pillars of this FDP, and as you all know, this is the online FTP. Mainly in these timings, that is 6 to 9, you are sharing with your families and all. So especially, I congratulate all the participants who are attending these FTPs over the past few days. So as the chief guest and our principals have said, we are expecting more researchers, okay, in this field of electric vehicles. I think some knowledge you could capture from this FTP, and we will always be welcoming you all in the coming FTPs and all. Okay, we will be looking forward more researchers and more purpose in this field and all. Okay, so once again, thank you all.
Thank you, Nitin sir. It was wonderful remarks from your side. Now, coming back to the end of the session, I welcome Eugene Mess to proceed with vote of thanks.
Okay, good evening, all. On behalf of the Department of Electrical and Electronics Engineering and Christ College of Engineering in Yankuda, it's my duty to give the vote of thanks on this memorable occasion of the valedictory function of Aicte-Atal sponsored FTP on electric vehicles to 29 August 2025. First and foremost, I express our heartfelt gratitude to AICTE and Atal Academy for granting us the opportunity to organize this FTP and for their consent, guidance, and support. Our sincere thanks to our esteemed chief guest of the valedictory function, Dr. T.D. Subhash of Zhejiang Ocean University, China, for gracing the occasion and for sharing valuable insights with us. And he is actually my PhD supervisor, and he is mentoring me to do all the activities which is related to the programs. So I once again thank you, Dr. T.D. Subhash sir, for guiding me, as well as coming to this FDP for delivering a session, and as well as for coming this function as a chief guest. I extend my deepest gratitude to our distinguished resource person, both from India and abroad, who enriched this FDP with their expertise, knowledge, and thought-provoking session. A special word of appreciation to our beloved principal, Dr. Sijo MT, and all the management, all the officials in the management for their encouragement and continuous support in successfully conducting this program. I also extend my sincere gratitude to Dr. Needu ma'am, Professor Nitin sir, and the entire EEE department for the continuous effort, support for this FDP, for conducting and organizing this FDP. Most importantly, my heartfelt thanks to all the participants from various states and institutions. Your enthusiastic participation, valuable interaction, and conservative feedback have been the real driving force for this success. And finally, as we conclude this one-year journey of learning and learning and knowledge sharing, I sincerely hope The experiences gained will share new research, collaboration, and innovations in the field of electric vehicles and sustainable mobility. And last but not the least, I thank my co-coordinator for this event, very silent co-coordinator, Vishnu sir, for giving all the support. That means from the beginning to the end. Giving all the support very silently and giving me the feedback. Thank you, Vishnu sir, for the for supporting me. I thank once again each and every one of you for making this FDP a grand success. Thank you all.
Thank you, everyone. Thank you for the valuable feedbacks and thank you for the valuable training. The sessions was just an inspiring, and I request everyone to end up the call. Thank you all.